This is the fourth in a series of 6 videos which try to explain something of the Higgs field and the way in which it can give mass to the known elementary particles. Someone who's studied mathematics or physics to around the age of 20, or who is reasonably familiar with most of the ideas shown here, should be able to work through the arguments presented in the 6 videos so that they have some grasp of the sophisticated concepts involved without having cut too many corners. A lot of new ideas will need to be introduced, and although these are no more difficult than the concepts shown here, they will require a good deal of work if they are to build up to a coherent understanding of the Higgs mechanism and to try and understand what's really going on. So, this part 4 is about spontaneous symmetry breaking of a scalar field, and we'll look at real then complex scalar fields, and this will lead to the idea that new particles seem to be created from the Higgs field, which we'll call Goldstone bosons. In previous sections we've looked at the standard model, dealing as it does with the known particles, forces and fields, apart from gravity, and we've looked a little bit at the Lagrangian approach to discussing the mechanics, if I can use that word, of the fields in the model. It turned out that in order for the standard model to have any validity, gauge invariance required that the gauge bosons, the force particles of the standard model, must all have zero mass. In practice, however, although this is true for the photons and gluons, it's not the case for the W and Z bosons, the force carriers of the weak force. With the elementary background of Lagrangian physics that we worked through, we should now be in a position to start to think about how these particles gain mass from what is called spontaneous symmetry breaking and the Higgs mechanism. Let's look in a bit more detail then at the Lagrangian for a free scalar field phi like the Higgs. Starting with a real scalar field, the Lagrangian density that we had for such a field phi was given by the difference between the kinetic and potential energy densities of the field, each of which is a function of the field. L equals T minus V, kinetic minus potential. We discussed what it meant for a field to have kinetic energy density and potential energy density, that is, energy per unit volume of space-time, and we came up with the following expression for Lagrangian density, the subtraction of the two. As we said, this Lagrangian density, which contains information about the way the field behaves, essentially has two parts, the kinetic energy density, and subtracted from this, the potential energy density. Looking at the kinetic energy term, we said that it relates to the rate of change of the field with respect to time and space, and actually contains 4 terms. These 4 terms show the rate of change of the field with time and the rate of change of the field with distance in the 3 directions x, y and z. To save writing these 4 things out every time, we use the shorthand form delta mu phi squared, where the subscript mu takes 4 values, 0, 1, 2 and 3 for time, x, y and z. Or even sometimes we'll write delta phi all squared, where the mu is understood. Looking at the potential energy, the constant mu here is of the phi squared term is not the same thing as the one in the kinetic term. In this potential term, the mu is related to the mass of any excited particle of the field. Once again, I ought to apologize that, like many others, I've used mu for 2 entirely different things in the same equation. I'll stress again, the mu in the derivative is an index running from 0 to 3, whereas the mu in the multiplier of phi squared is actually the mass of any excited particle from the field, equivalent to the m in some other versions of the Lagrangian that you may see. Still focusing on the potential energy part, the constant lambda in the quartic part of this is a dimensionless coupling constant and has to do with the field interacting with itself in some way, a kind of self-interaction. As the field interacts with itself, it turns out that potential energy is involved in that self-interaction. The other important thing to notice about this Lagrangian density is that it exhibits symmetry with respect to the substitution of the field with its opposite or negative value. So if instead of phi I was to substitute minus phi, I would get an identical Lagrangian density. This should be fairly obvious because all the phi's in the potential energy part are raised to even powers. So if each of the phi's goes negative, squaring them will give the same answer. Minus 1 squared is plus 1. The same is true for the derivative in the kinetic part. That is squared, so it will give the same answer if phi were to go to minus phi. In other words, we can say that this whole Lagrangian has symmetry around phi equals 0. Now, whenever a Lagrangian is symmetrical in this way, it usually means that something in the theory is conserved. It's a conserved quantity. Take that as a fact, if you will. This means that the operation of symmetry will not change that particular quantity. It's conserved. That's just by the way. Getting back to our free scalar field Lagrangian. Unfortunately, we can't write down numbers for mu and lambda in the potential part because we don't know them at this stage. And in our discussion, we're going to have to allow for some strange possibilities of them. We'll always take lambda as a positive number, but we will think a bit more openly about mu squared. For example, if mu squared itself is positive, then this term must definitely be negative. Ignoring the self-interaction term for the moment, we had earlier said that when a Lagrangian density has a negative field squared term in it, such as minus mu squared phi squared, then it means that the potential energy plotted against the field value phi has the usual parabolic shape, and the mass of any excitation will be real. Of course, if mu squared is positive, it would mean that mu itself could be positive or negative. But in either case, the mass mu is real. It's a real number. We might find it difficult to think about a negative mass, but positive or negative, it's real, providing mu squared itself is positive. Anyway, that's one possibility for mu. Real, positive or negative, because mu squared itself is positive. The other strange possibility that we have to allow for, however, is the situation if we consider that mu squared could be negative. This would mean that the term minus a half mu squared phi squared in the Lagrangian would actually be positive. There would be two negatives there. The Lagrangian would have a positive phi squared. In other words, the potential curve would be upside down. Now you'll know that for the square of something to be negative, then that thing must be imaginary. So if we're going to suggest that mu squared is negative, we're suggesting that the mass mu would be imaginary. What on earth could that mean? Well, as we hinted in previous sections, when we start to investigate the excited oscillator of the field phi, we use the picture of a ball in a U-shaped potential. We'll see that this means the curvature is in the wrong direction if mu squared is negative. Normally we would say that a particle is an excitation of a field. However, if the mass is imaginary, instead of the ball being in a cup, it will be on a hill. There will be instability, and any field excitation will spontaneously decay. In other words, there'll be no localized excitations of the field, no analogy to a ball going backwards and forwards in a cup, because there is no cup. This should be obvious when we discuss it all later. The idea of mu squared being negative might seem like a senseless suggestion, but it's not. Spontaneous symmetry breaking and the Higgs mechanism, which will lead to the W and Z bosons getting their masses, is going to come about precisely because we take mu squared for the Higgs field to be negative. In other words, we take mu in the equation to be imaginary. Okay, with this in mind, let's look at this Lagrangian in more detail. If we consider just the potential term, the potential energy density as a function of the field phi, we have a half mu squared phi squared plus a quarter lambda phi to the fourth. Remember, it's the negative of this that would be in the Lagrangian, kinetic minus potential. It's clear that this potential energy density of the field varies as the square and as the quartic of the field value, so it won't be a simple parabola. You probably already know that, generally speaking, anything that varies as the positive of the square of something will give a parabola going down and up. Anything varying as the positive of the quartic of something will give a shape that looks parabolic but will actually be narrower, if I can use that word, and will shoot upwards more sharply. Let's try and plot this whole function out with phi on the x-axis and the potential energy V on the y-axis. On account of the fact that mu and lambda can take a variety of values, we better pick some obvious ranges for them and plot a couple of graphs accordingly. Let's start with the case where mu squared is positive, not the unusual one. That's the straightforward one, and not the one we're going to need later. But let's look at it. It means that mu will be real, and we have the straightforward situation. Because we're always assuming lambda is positive, that means both terms in the potential are positive, the squared term and the quartic term, and they will both be made negative in the Lagrangian. Just looking at the potential, though, we'd expect the shapes of the squared and quartic terms to look something like this. There's the positive squared term going down and up, and there's the quartic term looking similar but a bit narrower. So for the moment we're assuming that the mass mu is real, positive or negative, but certainly mu squared is positive, and lambda is also positive. If you plot some numbers out in Excel for this, you'll see that you get something which actually looks parabolic. In a sense, the two shapes merge into one. It looks, for all intents and purposes, like a simple parabola. You don't really notice visually any evidence of the quartic term. This means that the plot for the potential V against phi then looks like this for mu squared and lambda both positive. We seem to have a simple quadratic looking function for V against phi. It doesn't seem to matter that there's a term to the fourth power. It still looks parabolic. It's still a kind of cup shape for both multipliers, mu squared and lambda positive. In other words, the mass mu of any excitation would be real. We will have localized excitations of the field as this ball, as we imagine it, goes backwards and forwards in the cup. Because the curvature of the cup is upwards, it means that the mass of any excited particle is real. You can also see, as expected, that this exhibits symmetry when phi changes to minus phi. It's totally symmetric around phi equals 0. Reflect it about the green line and you get exactly the same thing. Now stay with this for a minute and imagine a ball sitting at phi equals 0 in the cup at the place where phi equals 0. With the shape given, it means that the potential energy is a minimum at the bottom of the cup when phi equals 0. The potential isn't necessarily 0. We don't know the scale of the y-axis, but it's the lowest it can be. And if that ball were to go from side to side, its potential energy would go up and down. There would be an oscillation. There would be an excitation of the field. I want to stress something we talked about earlier. There isn't any actual ball moving around. There's nothing moving in space in this particular graph. The graph is depicting a single point in space-time. When I talk about the field going bigger or smaller, I'm considering here a single point in space. At this point, the field is going bigger and smaller over time. That's the x-axis of the graph. And the potential energy is going bigger and smaller accordingly. That's the y-axis. And it's showing how V varies with phi at that single point in space. Changes in phi around the 0 value will produce small oscillations at this place, which are perturbations of its physical state. In other words, slight changes in the scalar field phi will produce slight changes in the potential energy V and will give rise to a disturbance of the field. the adjacent point in space-time will feel this disturbance. If you like, that next door point will have its own plot of potential against phi, and on account of the disturbance, the field there will change. And as that point's field changes, it will go up and down the side of its cup. And this whole thing will continue from one point in space to another. And we can say that a wave or a particle has travelled outwards from the original point. In other words, taking mu squared and lambda both as positive means that the excited particle has a real mass. We can think of it as there being a kind of resistance to the field, or resistance that the field feels when it tries to increase. If you like, when the imaginary ball goes up the side of the hill, there's a kind of opposition to attempts to change the field from the point at phi equals 0 to a bigger or smaller value, and this shows itself as a kind of inertia to the motion of the ripple. It shows itself as the mass. In our Lagrangian, we can at this point ignore the self-interaction term. Not that it's unimportant, but at this point in this discussion of a real mass, it can be ignored. We then have the classic Lagrangian for the oscillation of a scalar field, a term in the derivative squared minus a term in the field squared. The minus sign for the field squared term in the Lagrangian means that the mass is real and the mass is given by mu. We'll find other situations later when this will occur, but from very different circumstances. In fact, the overall pattern of derivative squared minus a term in the field squared will be a clue to the existence of a particle with mass from the excitation of the field. That simple situation, an oscillating field in a kind of cup, was for the case that both mu squared and lambda were positive, the simple case. Much more interesting, however, is if we consider a different scenario. Still the same Lagrangian for the scalar Higgs field given by this formula, and we'll still keep lambda positive, but this time we'll make mu squared negative. Remember that this will mean that the mass of any excited particle is imaginary, whatever that means. Going back to looking simply at the potential term from the Lagrangian, that's the bit that would be negative in the Lagrangian, the shape of the curve for v against phi will again be made up of two parts, the wider squared term and the narrower quartic term, but one of them will now be upside down compared to before. With mu squared now negative, the squared term, the parabola, will be inverted. Again, if you put some numbers into Excel for this formula, this time you get a rather strange shaped graph which goes down, up, down, up. Here's practically the same plot as before, and you can see that it's the same numbers for x and the same formula, except that the squared term has been made negative, and this changes the shape completely. The reason for this is because for small phi, phi squared is very much bigger than phi to the fourth. So the upside down parabolic shape of the squared term dominates near the zero of phi, and we get the bump in the middle. But for large phi, however, positive or negative, the phi to the fourth term dominates and takes the curve upwards on either side, despite the upside down parabola trying to take it downwards. So the plot for the potential v against phi then looks like this for a positive lambda and mu squared being negative. Once again, this is symmetrical about the green line phi equals 0, which means that we can change phi to minus phi and nothing really changes as far as the potential is concerned. However, there's no way the field can be stable at phi equals 0. In our ball analogy, when the field phi goes to its zero value, the ball would be on a hill and would have to roll down. What we mean is that if the field were at the 0 point, x-axis here, on the hill, any very small change in the field value from 0 will make the potential fall away, and it will only really be stable when it reaches one of the minima on either side. That would mean that the field would settle in such a way that it was left with a value. In other words, it would not be zero. Let's call the values of the field that it could settle to plus V or minus V, as shown here. Some people use the letter F for this, but I'm going to go with V. So the field would have to have increased to the valley or decreased to the other valley in order for the potential energy to drop to one of the minima. The field phi in this case cannot settle at a zero value. That's why it's significant when we say that there is a Higgs field permeating all of space. In one sense, that's no big deal. You could say that there's an electron field permeating all of space. There's a photon field, there's a gluon field, and so on. But it's assumed that all of these other fields settle to values of zero when they're in equilibrium. Their lowest potential energy state is when the value of the field is zero. They're at the bottom of a simple parabolic type shape. Only when they're excited do they show themselves as vibrations and particles. The Higgs field, however, seems to be different. It permeates all of space with a value different from zero. It's in this side valley. Now it's very easy to work out an expression for the value of V, the field phi at the minima. You only need school mathematics to about the age of 18 to do it. It's clear, if you like, from the graph that there are three turning points, a maximum and two minima. And the standard way to investigate this kind of thing is to differentiate V with respect to phi, then make that differential equal to zero, and then solve what you get. So our expression for V in terms of phi is this. So it's just a case of differentiating this V with respect to phi and setting the answer to zero, then solving the equation that you're left with. Anyone, as I say, who's done basic calculus will find this fairly simple. If you try it, you'll be left with two possible values for phi for the minima, if you like, the two values. And these are given by plus V, which is plus the square root of minus mu squared over lambda, and minus V, which is minus the square root of minus mu squared over lambda. Don't be put off by the negative sign inside the square root. Remember that mu squared itself is negative, so it's actually the square root of a positive number. We can also write down this solution as V squared is minus mu squared over lambda, or lambda V squared equals minus mu squared. That relationship, however we write it, will be important as it will allow us to eliminate mu in later formulae by putting it in terms of lambda and V. Bear that in mind. Also, as we take mu to represent the mass in the Lagrangian, we can say that the mass is the square root of lambda V squared. This expression for mass will also come into play a little later when we look at excitations in the side cup. It will then be shown that the mass of those particles excited in the side cup will actually be a little larger than this value of mu. Anyway, we have found that this choice of a negative mu squared has led to this saddle-shaped potential and given us a minimum of a potential, a vacuum, which, although it's the lowest potential energy, doesn't correspond to the zero value of the field phi. Rather, it takes the value phi equals V plus or minus, as shown. This is known as the vacuum expectation value, or the VEV. This is not good, or at least it doesn't feel good. It surely seems sensible to expect that the minimum of the potential energy should correspond to when the field value is zero. It just seems reasonable to expect that. But that is not the case for this situation where mu squared is taken to be negative. Well, I suppose we might be able to fudge it in that direction, at least so that we can analyze some things. We won't change reality, but we'll be able to understand better what's going on, and that's what I'm going to do next. One thing about scalar fields is that you should be able to shift the value of the field by a constant amount and not change the physics of what's going on. This is tantamount to redefining the field, maybe giving it a new name, but making it equal to the old one with a constant added or subtracted. I'm going to call the new field eta, but it will be the old phi minus the amount needed to get the zero of it to coincide with the minimum of energy. In other words, let's make eta equal phi minus v. If you think about it, eta would then be 0 to the right of the hill at the minimum. Eta is 0 when phi equals v. Just check that for yourself. Eta is 0 when phi equals v. This means that the graph for potential in terms of eta is now given by this. Notice the new values, the eta values, on the x-axis of the graph and where the 0 is. What I've just done is not even a gauge transformation. It's the simplest of all global transformations. We're just subtracting a constant from the field everywhere. However, although it won't change the physics, it will allow us to see some underlying effects via the mathematics. It'll help to simplify the mathematics so that we can see what's going on. We know that the field will be in one of the values, so let's assume it's in the right-hand one here. Eta is 0 there, and there is stability. We can then think about that field in the valley as being excited and giving rise to a particle with mass, real mass this time, because it's in a cup. It's not sitting on the top of a hill with some kind of imaginary mass. It's now real. The first thing to notice, I suppose, with this graph of v against eta is that if you reflect it about this new 0, the new green line, you don't get the same thing. Instead of a bump and a dip on the left of 0 like we've got here, you'd have a bump and a dip to the right of 0. It's not symmetric with respect to changes of plus eta, from plus eta to minus eta. In rolling down the hill, if I can put it like that, to find the lowest potential, it has spontaneously broken the symmetry. In order, therefore, to go a bit deeper into all of this, let's take the old scalar field Lagrangian density and somehow see what it would look like for eta. Here's our original Lagrangian with phi in it. We won't get rid of the self-interaction term straight away because it may, and in fact it does, affect the analysis of the shifted field. Let us, however, substitute for phi to get the Lagrangian in terms of eta. In other words, we'll put phi equals v plus eta into the Lagrangian for phi. Doing this would give this formula. The field is now eta, and v is just a constant addition. Looking first at the derivative part of the Lagrangian, the kinetic term, it should be obvious that the added constant v won't affect it in any way. Being a constant, its rate of change is 0. So the phi here can simply be written as eta, and we'll have the derivative of eta squared instead of that of phi. As far as the term on the right is concerned, the potential energy term, the substitution of eta plus v is also fairly simple. It's just a case of multiplying the brackets out, then sorting out all the terms. And if you do this, and at the same time eliminate mu squared, as we suggested earlier, by using the relationship mu squared equals minus lambda v squared, you get for the new Lagrangian density for the eta field, L dashed equals this formula. Multiplying out those terms gives something that looks a bit more complicated, which expanding the last bracket gives something even more complicated. However, even though it looks very messy, if I highlight some of the similar terms, if you look carefully at this, you should see that the yellows disappear, the greens are constant, and therefore we could ignore them in the Lagrangian. They're not going to change anything, they're just constant. The reds add up, and the blues add up, leaving us with the formula for L dashed, or putting these terms into an equivalent potential bracket, it gives this final expression for L dashed in terms of eta. As before, the quartic term in eta means that the field interacts with itself. And the same is actually true for this cubic term which has appeared. Not that these terms are unimportant, they are very important for many aspects of Feynman diagrams and understanding what's going on, but for this discussion of the Higgs, we can now afford to let them go. We didn't ignore the quartic term at the start of this analysis because, in fact, it has contributed to changing the Lagrangian in a very important way. Anyway, this is what we're left with if we ignore the self-interaction terms. This time, instead of having a positive field squared term in the Lagrangian indicating an imaginary mass, a ball on a hill, we're left with what is definitely a negative field squared term, meaning the mass is now real. That, of course, is to be expected given the fact that we now have the potential resting in the cup-shaped valley to one side. This is the Lagrangian density L dashed of this new field eta. Just to emphasize the importance of this negative potential term for mass, you may recall that when mu squared was positive and we were dealing with the simple Lagrangian, it was this formula. And in that case we had a simple parabola looking curve and we had a real mass mu. Now compare these two. The original simple Lagrangian in a simple parabola and the new one in this side cup. The equations have the same kind of form. The original, phi without any self-interactions in a normal parabola, represented a real mass in a U-shaped potential well, whereas the new one, eta without any self-interactions, represents a real mass in a sort of U-shaped potential well to one side. We can show them with our imaginary ball in the relevant cup to help imagine any excitation. Any excitation of these will oscillate about the zero of their relevant field, and the mass of that excitation will be real. In each case, a real particle with real mass will come from the point where the field is disturbed. However, there will be a difference. Let's look at the mass term in more detail. For the multiplier of the phi squared in the simple situation, we had a half mu squared, where mu was positive for that one. It was in the cup of the parabola shape, and mu was identified as the mass of the excitation. For the multiplier of the minus eta squared term in the symmetry broken case, where we're talking about the particle from the Higgs field, we have lambda v squared. By comparing the two parts of the equations, we can see that lambda v squared must represent what a half mu squared did. Lambda v squared, if you like, is equal to half mu squared, or lambda v squared is equal to half the mass squared, where m is the mass of the particle in the side cup. So that for this new excitation in the side cup, the Higgs boson, the mass will be given by the square root of 2 lambda v squared. You may recall, however, that when we started this analysis and worked out the residual field V, we had an expression for mu, the size of the mass before symmetry breaking, which was the square root of lambda v squared. So that the mass of the Higgs particle in the side cup turns out to be root 2 times larger than the original mu, or mass, before symmetry breaking. The mass of any excited particle in a side cup after spontaneous symmetry breaking is root 2 times the mass of the particle before symmetry breaking. So nature, having broken this symmetry and the potential having settled to the minimum value at one side, it means that the Lagrangian is now respectable. It doesn't have that strange, imaginary and unstable mass excitation from sitting on the hill. It has a minimum potential, a vacuum, when the field eta is at 0. And also the field has a mass term of the right sign in the Lagrangian. It's negative. And so the mass of the excited scalar particle is now real, if a little larger than we'd expected. If this scalar field is the Higgs field, then any excited particle from its side cup could be said to be the Higgs boson, of what we now know to be a mass of 125 GeV, as discovered in 2012. Now it's worth mentioning that the physics embodied in this new eta Lagrangian, which helped us to understand things, can't actually be different from the physics we had when we said we had phi in it. Simply shifting the field by a constant amount everywhere doesn't change the physics. The actual Higgs field is still not zero everywhere in space. It's still phi. And it has a value of plus v or minus v, I suppose. Using eta simply helped us to understand the mathematics and to interpret things. The field phi has settled at the value of plus v or minus v to give the potential its minimum. And around that particular field value, let's say plus phi, the potential is not symmetric. The symmetry has been broken. Nature has spontaneously broken it by insisting that the potential reach a minimum. It must be fairly obvious, though, that in some ways the symmetry is still there. Looking at the potential, you can see that there is a kind of symmetry, but it's not around the value that the field has settled at to get to the minimum potential energy. In fact, we say that because of the way things have settled, the symmetry is hidden by our choosing a value of plus v for the original phi to be the vacuum. In physics language, the old Lagrangian of the field produced what is called degeneracy, which in this case means that there were two values of the field that correspond to the minimum for the potential, the vacuum. In choosing one of these values of the field for the vacuum, we have effectively hidden the symmetry. I suppose as an aside, one could ask the question, is settling to phi equals plus v any better or worse than settling to phi equals minus v? And the answer is no. They are both taking the potential energy to exactly the same minimum value, and in that sense they're identical. Somewhat like trying to balance a pencil on its point, the unstable equilibrium on the hill of phi equals naught means that it can go either way, and any final position is no better or worse energy-wise than the other. A second question could then be, given that this picture is for one place or point in space, and there's no difference as far as potential energy is concerned between plus v and minus v, could different places next to one another in space have plus v and minus v? Could different places settle to different values of the Higgs field? And the answer is, again, no. You cannot have all the different points in space going randomly to plus v or minus v, even though there's no difference in potential energy. But why not? Well, granted, as far as potential energy is concerned, that would be fine. Either side gives the same minimum of potential energy. But you have to ask the question, what about kinetic energy? Remember that the Lagrangian density is given by the kinetic term and minus the potential term. If you have adjacent points in space at different minima, one at phi equals plus v and the adjacent one at phi equals minus v, you have a difference in phi of 2v over a very short distance. This means that the rate of change of phi with distance, x, y, or z, or even time, is very, very large. The field phi would have to change very suddenly in going from one point to another. There's no way it can be a gentle change from plus v to minus v. If the two adjacent places are separated in the x direction by a small distance, then d phi by the x will be massive, which means one of the four contributions to the kinetic energy term d mu phi all squared will also be massive. The potential energy may well still be at a minimum if different places are at plus v and minus v for phi, but the kinetic energy will not be at a minimum. So no, the only way really to minimize the energy is for every point in space to come to the same decision, either plus V or minus V, no mixture. And that is what is believed would happen in this case of a real scalar field. Adjacent points would sort themselves out so that everywhere is either plus V or minus V. Now, before we move on, let me state simply what we've got so far. The Higgs field is a scalar field, no direction to it, and it's a simple real number at this stage. It also has the rather strange property of a negative mu squared in the potential and hence also in the Lagrangian. That would mean an imaginary mass for any excited particle from the field, but that situation doesn't actually happen because spontaneous symmetry breaking takes place. The field moves to and then sits in the valley to one side, and any excited particle from the field now has a real normal kind of mass of value √2 times what we might have expected. The other important conclusion, of course, is that the Higgs field is not zero throughout space, but has a value of V, or maybe minus V, where V is given by mass of the Higgs over the square root of 2 lambda. Or you could say the mass of the Higgs is the square root of 2 lambda V squared. That's fine, but it doesn't seem to have moved us forward in understanding why the W and Z bosons get their mass from the Higgs field. All we've shown is that in some way the Higgs boson is excited from the Higgs field, not in the normal way of sitting in a simple cup at the field value of 0, but from sitting in a side arm of the more complicated potential relationship. We found a way to understand it better by imagining a different field, eta, with a shift at 0, but we recognize that the actual field is still phi, and will have a value of plus V or minus V everywhere in space. The Lagrangian we used for this scalar field phi was fairly simple, a kinetic part minus a potential part. And the symmetry of this, when it wasn't hidden, was simply from the fact that if phi was changed to minus phi, it stayed the same. There was, if you like, a simple mirroring around phi equals 0, the green line. This requirement that things shouldn't change for changing phi to minus phi is a very basic requirement. But we now want to introduce something more stringent. At the same time, we will explain another complication of the Higgs field. This is the beginning of where I said things would grow arms and legs, in the sense that the actual field phi is not as simple as we've discussed so far. The Higgs field is not to be represented simply by a real number. It's actually a complex scalar field made up of a real part and an imaginary part. We can write it as the mixture of two real scalar fields, phi1 and phi2, one of which is multiplied by I, the square root of -1. Here's the complex representation of the field phi as we should have represented it. Phi equals 1 over √2 into phi1 plus I phi2. For simplicity, from now on I shall ignore the 1 over √2 and write this as phi equals phi1 plus I phi2. In fact, I may ignore multiplicative factors a lot in what follows. They're less important for understanding what's going on from now on and can simply clutter the equations. I had to keep them up to this stage. For instance, I needed to keep the half and the quarter for our real field Lagrangian because they were crucial in changing our positive mass term on the hill into a negative mass term in the valley for the mass of the Higgs. That kind of thing will not arise again in what follows, so I can almost ignore multiplying constants. Anyway, I'm saying that I will define a complex Higgs field to be phi equals phi1 plus I phi2. What this is saying is that at every point in space, the field has a real value and an imaginary value. Those familiar with complex numbers will know that they can be represented on a plane, where you show the imaginary numbers at right angles to the real numbers. This means that the value of phi at a point in space could be expressed as lying somewhere in this complex plane. As an example, the diagram here now shows a blue dot at the value of the field phi equals 3 minus 4i. It has a real value of 3, an imaginary value of minus 4. Of course, this picture of a plane doesn't mean a plane in physical space. We're still talking about a single point in space. But we have to imagine a kind of invisible space, for want of a better word, within that point where the two values of the field reside. Now let me remind you of some maths. For every complex number, we can write another number called its complex conjugate, where the imaginary part is multiplied by minus 1. So if phi is equal to 3 minus 4i, the complex conjugate of it, which is written as phi star, is equal to 3 plus 4i. Furthermore, in order to calculate the square of a complex number, you have to multiply the number by its complex conjugate. And this always gives a real number for the answer. For instance, phi star phi, or phi squared if you like, for this number would be 3 plus 4i multiplied by 3 minus 4i gives 25. The imaginary parts disappear. You can probably see by comparing this with the diagram that because the I terms disappear, the square of what you might call the radius is equal to the sum of the squares of the real and imaginary parts, 3 squared plus 4 squared. In fact, the whole thing is just Pythagoras. The size or magnitude of phi could then be shown as a radial line on the diagram of size 5, square root of 25. In fact, there will be lots of different complex fields with different values of phi 1 and phi 2, which have an absolute value of 5. And they could be shown as lying on a circle of radius 5, shown here in mauve. This hints at another way we have of representing complex numbers. This relates to the idea of the radius of a circle, and it's going to be important in our analysis, so I'd better say a little bit more about it. When a field is represented by the two numbers phi 1 and phi 2, it's simply representing, as I said, one point on this imagined plane. Two numbers for one point. So we say that the field phi is phi 1 plus I phi 2. Phi 1 and phi 2 could be any values depending on the size and makeup of the field. In our example, they were 3 and minus 4. However, we could equally well represent that point on the imagined plane with two different types of numbers by using a different system. We call it the polar coordinate system, and the two numbers are called polar coordinates. For example, the point 3 minus 4i could equally well be represented by the radius rho of the circle it's on and by the angle omega that the radius has from one of its axes, let's say from the real positive axis. We would then say that the field phi at that point is given by rho times e to the I omega. In this diagram, rho, the radius, would be 5, and omega here would have to be around 307 degrees or 1.7 pi. So in dealing with the complex scalar field phi, we can either say it has two components, phi 1 and phi 2, and work in Cartesian coordinates, or if it's better to work in a circular situation, we can say that the field has two components, rho and omega, and do all our work in polar coordinates. We can talk as though phi1 and phi2 are fields, or we can talk as though rho and omega are fields. In each case, we'll be describing the complex field phi. It turns out, as I said, that the polar coordinate method will be very useful later on in making the analysis simpler to do. However, going back to the idea of a simple real scalar field, not complex now, which had only one number to represent it, you may recall that Lagrangian density contains some squares of the field and was of this form. It should therefore not be surprising, I hope, that the Lagrangian density for a complex scalar field phi is given by this formula. You should be able to see that it looks much the same, but the squares of the old field have now been written differently to accommodate the fact that we're dealing with a complex field. Phi squared is now written as phi star phi, and phi to the fourth is phi star phi all squared. You can only get the square of a complex number by involving the complex conjugate. Also, however, the square of the derivative is written slightly differently, but you should be able to see again that it's really the same thing, but for a complex field. The squares in the new Lagrangian will be calculated by multiplying the field by its complex conjugate, either using the Cartesian coordinates, where we say phi1 minus I phi2 multiplied by phi1 plus I phi2, or by using polar coordinates, if that helps, where we'll say rho e to the minus I omega times rho e to the plus I omega, which will give rho squared. Right, now that we have all that sorted, we need to go through all the same procedures as before and look at the Lagrangian density for this kind of complex scalar field, and particularly focus on the potential. If you remember, when we did it for the real scalar field, the simple case, we took lambda to be positive and mu squared to be negative. That particular potential gave this red line for the plot of potential energy density against field. The fact that phi was real in that case, not complex, meant that we could lay out the values of it on a single axis. Here it's the x-axis. Remembering, however, that the new phi that we're moving over to is now complex, it shouldn't surprise you that if, as before, we take lambda to be positive and mu squared to be negative, the values that gave the bump in the middle, then the potential for the new and complex field phi will give, instead of a single axis at the bottom, a plane, and instead of a red line above the phi axis, a red surface above the phi plane. Here it is. This is sometimes called a Mexican hat potential, and it tends to be drawn like this, with the top sliced off, not showing the higher values of V. I hope it's obvious that the straight line of the old phi axis has now become the phi1, phi2 plane in this imaginary space. Otherwise, this is, in many ways, exactly the same shape as before. It's just a three-dimensional version of the red line with two valleys and a hill in between. But now the two valleys form a circular channel in this imaginary kind of space. I should stress again that this diagram represents a single point in space, or even space-time. Every point, everywhere, in effect, has one of these diagrams to represent the phi field, the Higgs field, at that point. Also, I hope it's obvious that you could do the same kind of exercise as before to find the minimum point in the valley, the distance it will be from the center zero. You just take dv by d phi, differentiate, put it equal to 0, and solve the resulting equation. Okay, the field is in two dimensions. But it still involves differentiating the potential with respect to field, equating it to 0, and then solving for the value of phi to give the turning points. And it turns out that it gives exactly the same answer as before. The value of the radius in the valley of the Mexican hat, which is the value of the field when the potential reaches its minimum, is given by v, where v squared is equal to minus mu squared over lambda. Remember, mu squared itself is negative. So apart from the solid shape, it would seem that this complex scalar field situation is very similar to the real scalar field case. In terms of symmetry, however, there's more to it than there was before. The symmetry for the real field was from the fact that if phi changed to minus phi, the potential energy stayed the same. It was a simple mirroring across the green line at phi equals 0, a simple shift in the value of phi. Now, however, with the complex phi field, the potential will stay the same if you go in a circle with phi, if I can put it like that. For example, the mauve circles here illustrate some lines of constant potential. As you move around any circle like this around the complex plane, changing phi 1 and phi 2 but keeping the radius the same for a particular line, the potential will stay the same. You won't go up or down the sides of the valley. Go around at any level of v and it will be constant at that level. It will be invariant. In fact, the whole Lagrangian will be invariant as well, not just the potential. The whole Lagrangian of this complex field will be insensitive to this kind of rotational change in phi. Now this can be expressed mathematically by saying that the Lagrangian is invariant, or remains the same, if you modify the complex field by a phase transition, giving it a constant phase shift of, say, alpha. So phi goes to phi dashed, which equals the old phi times e to the I alpha. As I say, in other words, if the field phi is multiplied by e to the I alpha, nothing really changes. This is not just a simple mirroring, not just a simple shift in values like we had before. This is a continuous transformation law of the field. And the Lagrangian is still symmetric or invariant under this continuous transformation. If you like, nothing changes as you move around a circle. This kind of mathematics looks unfamiliar, don't worry. Multiplying phi by this term e to the I alpha simply means rotating phi around the complex plane by an angle alpha, keeping the same radius. In other words, it goes around the circle. For example, multiplying the field by e to the I pi will take it round half the circle, whilst if I went round e to the I 2 pi, it would take it back to where it started, the whole circle. What we're saying is that changing phi in this way makes no difference to the potential, or indeed to the whole Lagrangian. So repositioning the field from phi to phi dashed anywhere along the same circle doesn't change things. You might even be able to see this from the mathematics if you look at the Lagrangian for the complex field. Whenever you have a phi on the potential side, to the right here, it's always multiplied by a phi star. So if you were to change phi to phi dashed, if you multiplied it by e to the I alpha, you'd also have to multiply phi star by e to the minus I alpha. And when you multiply the two together, e to the I alpha times e to the minus alpha, e to the I alpha times e to the minus I alpha, you would get 1. In other words, they would cancel out. So there's bound to be no change in this potential part. And this is also true of the derivative term, if you care to look into it. Now, we said earlier on that whenever a Lagrangian has some kind of symmetry, it usually means that something in the theory is conserved. This means that the operation of symmetry will not change that quantity. This particular kind of symmetry is called global U1 symmetry. Global because exactly the same thing is done to the Lagrangian at every point in space. In other words, if you were to rotate by 45 degrees or pi by 4 in one place, you'll also rotate by 45 degrees everywhere else. Don't forget, this picture of the Mexican hat can be thought of as being for a single point in space. All other points in space have their own Mexican hat. Change them all by 45 degrees or whatever, and the world doesn't change, if I can put it like that. Now, we are assuming, as before, that lambda is positive and that mu squared is negative. The negative mu squared means that initially, at phi equals 0, on the top of the bump in the Mexican hat, any excited particle has imaginary mass, because it sits on the hill of the Mexican hat potential in the middle. It has a kind of negative resistance to any attempts to move it from the origin, where the field phi is 0. This means, in a way, it doesn't resist. It actually falls away from that point into the valley which goes around the hill. Once it gets there, it then has a real mass as it sits in the U-shaped valley. In some ways, this seems no better than before. At least before, with a real field, we had just 2 minimum points for the field value to fall down into. Now with the complex field, we have a circle on the complex plane, and so there are an infinite number of minima for the potential, which the field can settle at, an infinite number of places around the valley. Within that circle, or channel, at the bottom, however, not only will the potential be constant, but obviously the radius will be constant. We also know that the radius squared will be equal to the field value squared, ignoring again any 1 over root 2, and will be given by the square of the sum of the real and imaginary parts. Phi squared equals phi 1 squared plus phi 2 squared, which equals v squared. But from our relationship, v squared equals minus mu squared over lambda, and that means that the value of the field squared is given by minus mu squared over lambda. So, having looked at this more accurate representation of the field using the idea of a complex field, and having hotted up the symmetry requirement, this will now allow us to state Goldstone's theorem, which is a key element in understanding how the W and Z get their mass. Don't worry, we're getting there. When we had the real scalar field, the simpler case, we did some extra maths in order to understand what was going on. We shifted the field, or redefined it, to eta, so that the zero of it was at the minimum of potential, and we analysed the system from there. We ended up finding out what kind of fields were hanging around. Well, we need to do that kind of maths again. That would involve shifting the field to somewhere in the valley like this. Anywhere in the valley would do. We would add real and imaginary bits to phi to get it somewhere in the valley. However, it's quite messy to do it that way. And in actual fact, there is a simpler way of going about this problem. We can make use of the fact that we now have rotational symmetry. So I intend to change to polar coordinates and to tackle the problem from that point of view. It will be easier. Now we could at this point launch into the mathematics of polar coordinates applied to this system and see what comes out. However, I thought it might be better simply to explain the kind of results that we're likely to get. In other words, having got our picture of the relationship between potential energy and the field value, the Mexican hat, we could simply just think about what might happen to the field. So in that kind of spirit, I will first of all go through the descriptive hand-waving explanation as to what this strange potential shape will do. If we can make sense of that, then we can try the mathematics, which should give the same kind of conclusions that the hand-waving descriptive arguments give. So, putting the mathematics on hold, here's a descriptive discussion. For a point in space with this field configuration, we understand that the field value will settle somewhere in the valley, some radius from the peak. Think of the ball analogy if it helps. Just as before, the field value can vary, and if it varies like this, we will have exactly the same kind of situation as before. Here, as the field increases and decreases at this point in space and at this point on the Mexican hat, the potential energy will go up and down, and the vibrating field will disturb the neighbouring space point, which also have Mexican hats like this, and they will begin to oscillate. In effect, a quantum wave will be transmitted, or if you like, a particle will travel through space. In the situation as I've drawn it here, the value of phi looks as though it's negative imaginary, roughly, and it's oscillating. But I could have placed it anywhere around the valley, in which case phi could be a mixture of real and imaginary parts vibrating. In other words, the ball, if I can put it like that, could be anywhere around the valley and have both real and imaginary parts vibrating as it goes in and out radially. The blue lines in this graph illustrate that more general situation. Here I've drawn phi1, the real bit, somewhat larger than phi2, the imaginary bit, although they could have been the other way around. It depends where you put it in the valley. I'm plotting things against time, so we're taking a single point in space, x, y, and z, and plotting the field against time. I've also shown in red how the potential energy changes during the oscillation. As the field oscillates up and down the inside of the hat, up and down the sides of the valley, the real part of the field and the imaginary part will oscillate in phase with one another. And you can see this clearly from the two blue lines. As far as energy is concerned, of course, there are two types of energy to the oscillation. There are kinetic energy changes from the way the field stretches in space and changes with time, but there will also be potential energy changes as the field goes up and down the sides of the valley, if I can put it in that way. The potential energy varies as phi squared, so it will change at twice the frequency of the oscillations, as shown here in red. The potential energy will vary in such a way that it is a maximum when phi is a maximum or a minimum. And it's pretty clear that any particle that's transmitted from this disturbance will have potential energy involved in its oscillation. The particle will have mass, if you like. I say that because there's another way that the field value phi can change at this point in space, in this Mexican hat. It can go round and round. This is the descriptive bit. This doesn't involve potential energy, because that is constant in the valley. It can go on and round without involving changes in the potential energy at all. Now you may think that's not really a vibration, but think about it. As our imaginary ball goes around in this alternative way, what's really happening is that the field is changing. Negative imaginary, as in this picture, then positive real as it goes round to the back, then positive imaginary over to the right, then negative real, and so on around and around. In fact, assuming a constant velocity round the circle, both the real and imaginary parts of the field would oscillate sinusoidally as before. But here's one difference to the previous type of vibration. They would always be equal in amplitude, and there would always be a phase difference between them. Once again, this changing field will have kinetic energy and will disturb the neighbouring space points, and they will begin to oscillate in the same way. There will be a quantum wave, in effect a particle, travelling through space. The other difference, of course, is the fact that the particle from this vibration has no mass. When the field changes or vibrates in this way, It's like as though the ball is going along a flat surface around the valley. The potential energy doesn't change, it's constant. That means the particle from the excitation is massless. Here's what the oscillation at this point might look like as a plot against time, with the real and imaginary parts in blue again. Note that I've also shown the potential energy to be constant and unchanging. This is a kinetic wave only. Now this may seem weird. Instead of the possibility of one type of oscillation and therefore one particle being generated, which we had in the real field case, we now have two possible particles for this complex field with broken symmetry. Now, of course, it's not the idea of the complex field that's done this, that's given us two particles, because even if we had a simple parabola-shaped potential and we allowed the field to become complex, any vibration within that paraboloid cup would still only be of one type of oscillation. There would be a mixture of real and imaginary parts vibrating in phase, with the potential energy varying at twice the frequency, and the generated particle would have mass, but only one particle. It's only when the symmetry is broken and the field is complex that we get this Mexican hat, which means the field drops into the side valley and we get two types of vibration, two types of particles. We not only get the original particle with mass from the radial vibrations, but also the extra massless particle from the changes around the circumference. Let me emphasize that in this case, the two particles are very different from one another. They both obviously have the complex scalar field phi oscillating, but one of them, the extra one, does not involve any changing of the potential energy in its oscillation, and hence it does not have mass. It is also not found in nature, so something else must be going on. But for the moment we'll ignore that and think in terms of there being an extra particle or vibration in this situation. The oscillation of the two particles here are different too. The original particle, if I can call it that, has some field values simply going bigger and smaller, the real and imaginary parts being in phase. It gives and takes energy as the field vibrations proceed. Our picture was that of a ball radially going up and down the sides of the inside of the valley. This implies that the particle has mass, and it would appear to be a normal massive boson of spin 0, which we might call the Higgs boson. The mass will be given by the same formula as we calculate for the real field case. The mass of the Higgs is root of 2 lambda v squared. The second particle seems to have appeared out of nowhere, and it came about because of the symmetry breaking of the complex field. It has the field value fixed in magnitude, phi squared is constant, the radius squared, but it continuously changes its real and imaginary parts. No potential energy is involved in the vibrations of the field in this way, which generates this particle. Our picture was of a ball rolling on a flat surface around the valley. And all this implies the creation, if I can use that word, of a massless scalar particle. The extra particle is a massless boson of spin 0. And we can now state the Goldstone theorem for this complex field, which says, or one version says, the spontaneous breaking of a continuous symmetry of the Lagrangian generates a massless scalar. It corresponds to fluctuations around the chosen vacuum in the direction described by the neighbouring vacua. So, that's the descriptive explanation of what might be going on with this Mexican hat potential. It should be obvious that the mathematics should predict all this. It should be able to predict the creation of this Goldstone boson. We should be able to see it in the maths. I said earlier that I would go through the maths of that, so here goes. In other words, let's see how the mathematics predicts not just the usual Higgs boson with mass, but also predicts the new massless Goldstone boson. We'll do this in 2 stages. First, we'll change to polar coordinates to make use of the rotational symmetry and make the calculation easier. And then we will shift the zero of the field from the center of the Mexican hat to the valley. And hopefully, by that point, we will be able to see the 2 particles in the mathematics. Recall that the Lagrangian density of a complex scalar field is given by this expression. Remember too that in polar coordinates, phi and its complex conjugate phi star are given by rho e to the I omega and rho e to the minus I omega. And the square of phi is given by rho squared. So if I take the expression for the complex Lagrangian density and substitute for phi and phi star these values in polar coordinate, the polar coordinate expressions for them, it gives me this expression. This time you'll notice there are 2 variables in each of the derivatives. There's a rho and an omega. So we're going to have to differentiate these by parts. Now that's not difficult, and if you do it and then simplify the rest by remembering that e to the I omega times e to the minus I omega is equal to 1, it simplifies right down to this expression. Multiplying out these brackets, we can at the same time make the substitution that mu squared equals minus lambda v squared. If you remember, we did that last time. That was an expression we found from where we found out the minimum of the valley, where the valley was. We did the differential and got that relationship. So get rid of mu squared by putting minus lambda v squared in. This will then give, for our Lagrangian density, this expression. We can now gather terms, which gives this, and then rearrange them, which will give my final expression at this stage for the Lagrangian. Now that may seem a bit long-winded, but all we've really done is to show what we already knew, but in a different set of coordinates, polar coordinates. This is still the situation before symmetry breaking takes place. In other words, while the ball is at the top of the Mexican hat. Remember, it's the derivative part of the field in the Lagrangian that identifies the existence of excitations of fields or particles, their kinetic energy. And this expression clearly shows the existence of 2 such derivatives of fields. There's the d rho squared, which must be associated with 1 boson. In fact, it's the radial movement. Rho is the radius, it's the radial movement. And there's d omega squared, which must be associated with the angular movement. The radial field has the derivative squared in d rho squared, delta rho squared, of the radial motion, but it also has a positive field squared term in it, in rho squared, indicating, of course, an imaginary mass. This is what we might call the unstable situation, where the field is on the hill, so we're not there yet. The Lagrangian also shows the rotational field derivative squared term in d omega squared of the motion around the valley. This has no mass term associated with it. There is no term in the Lagrangian in omega squared. So this is obviously the angular oscillation of the field, which will manifest itself as a massless Goldstone boson. There's no omega squared term. Finally, we still have a self-interaction term in rho to the 4th, which we can't ignore just yet. We can't get rid of it because it will contribute in other ways as we shift the field to the valley. So that's what we need to do. We need now to do the equivalent of shifting the zero of the field. This time we need to shift it from the center zero on the hill into the valley where the potential is a minimum. Anywhere in the valley will do. Essentially we need to define a different field and work with that, a bit like we did with eta in the real field case. Instead of going that eta route, perhaps the best option is to recall that ρ, the radial value of the field, will be oscillating only very slightly, nowhere near as much as is shown here, but the radius ρ is clearly a variable. It's changing. Once in the valley, it will sit at or near the value v, our known radius, and it will go slightly bigger and smaller as it oscillates. As I say, the distances in this picture are exaggerated. The valley will have very steep-sided walls, and any change in potential will happen for a very small change in radius. We can therefore define a new field, which we'll call H for Higgs, where ρ, the actual radius at any instant, is equal to v, the constant radius in the valley, plus a very small amount due to any radial vibration. We can then see that as h goes positive and negative, ρ will go slightly bigger and slightly smaller, representing the Higgs particle excitation in the valley. Here's our Lagrangian that we need to substitute this value of ρ into, where I've highlighted the radius in red. This substitution should be fairly straightforward, again if a little messy. The first term in delta ρ simply becomes delta h because the v is constant, but all the other terms will be altered in some way. In the case of the third term, because of the fact that ρ is more or less constant at a value of v, and in this term it is a simple multiplier, then we can legitimately replace this ρ squared by v squared. In the case of the remaining two terms, however, this is not really an option. The reason is that some of the extra terms that come out of the second term when ρ equals v plus h is substituted will be very similar to some of the extra terms that come out of the fourth term. Things will add up or subtract and change in some way. In fact, it's these changes that will make the positive mass term sign become a negative one, meaning that the mass of the Higgs will be real and in the valley. Anyway, if you make these substitutions for ρ equal to v plus h, the Lagrangian becomes this. It should be obvious that once these brackets are multiplied out, many of the terms can be combined. This is why we couldn't ignore the self-interaction term earlier on, and we certainly couldn't simply replace ρ by v in these two terms. Once these brackets are expanded, we can ignore any constant terms, those without h or omega in them. Gather things together and shuffle them around. This will leave us with the following expression. You should realize at this point that the two components of the field, or the two fields, are h and omega. H is the radial vibration and omega is the angular changes. These cubic and quartic terms in H can now be ignored as self-interaction effects, leaving us with, now we are there. Once again, this clearly shows the existence of the two fields, two distinct derivative terms, one in H and one in omega. This time, however, the Higgs field expressed by the field H has a real mass, signified by the negative field squared term, the one in H squared. And also the Goldstone Boson of the field omega, once again, has no mass term. So that's it. That's the maths bit over and done with. We've shown by the mathematics what seems sensible from imagining how the field could shift around in the Mexican hat potential. It's clear that the spontaneous breaking of the symmetry of the complex field has left us with not just one spin zero boson, but two. We got the expected Higgs boson with mass, but we also got the perhaps unexpected massless Goldstone boson. This, as we said earlier, is an example of the Goldstone theorem, which can be written as the spontaneous breaking of a continuous symmetry of the Lagrangian generates massless scalar particles. Also, we should remember that the expression for the mass of the Higgs comes from the multiplier of the field squared, h squared, in the Lagrangian. So if we compare the Higgs part of our new Lagrangian to the usual one for a scalar field with no self-interactions, once again we can see that lambda v squared is in the place of half mu squared, which means that if we equate them, it gives lambda v squared equals a half mu squared, or half m squared. And of course, rearranging that to get the mass of the Higgs boson, we can say once again that the mass of this radial excitation particle in the valley will be given by m Higgs equals the square root of 2 lambda v squared. When the mass of the Higgs was measured by experiment in 2012 to be around 125 GeV, and it was known that the value of V is of the order of 246 GeV, it was then possible to estimate the value of lambda, the Higgs coupling strength, and it was found to be around 0.12. This Higgs self-coupling constant also affects the production rate of Higgs particle pairs in experiments. Well, we still haven't arrived at really thinking about how the W and Z bosons get their mass. All we've done is show that this complex scalar field, after symmetry breaking, produces not only the usual particle with mass, the Higgs, but also a massless Goldstone boson. We need to make one more modification, and we're there. Although it makes it much more complicated, we'll deal with it in a very simple way, without the mathematics. The complication which we need to add, which we'll deal with in the next video, is the fact that the simple singlet complex field that we've been working with, phi equals phi1 plus I phi2, is not enough. The Higgs field does not simply contain two components, phi1 and phi2, or if you prefer, omega and rho. Rather, we need to be thinking about a field which has four components, four values at every point in space. It has to be described by what is called a complex doublet field. We'll move on to this in part 5, the 5th video, and it will be then that we'll be able to nail the idea of the Higgs field giving mass to the W and Z bosons. It will be all to do with the idea of not just one extra Goldstone boson being produced from spontaneous symmetry breaking, but 3. But that's for next time.